This is the 18th in a series of lectures on differential geometry. In this lecture, we'll study Sard's theorem, which tells us that we can avoid having critical values. We can stay away from critical values of smooth maps. Of course, smooth maps may have critical values, so there can't be none of them, but we want to stay away from them. So let's think first about what we mean by staying away. We're going to try and avoid things by saying that we can get away from them if they don't take up too much space. So we'll say that a set contained in Rn has measure 0. It's said to have measure 0 if it can be covered for any epsilon greater than 0 can be covered by a sequence of boxes whose volumes sum to less than epsilon. By and large, I won't prove much about measure 0 sets. I'll hope that you've seen them in other classes. I'll state the results that we need, but I won't prove very many of them. A simple example is that in the plane, the horizontal axis has measure 0. In a picture, what you imagine is putting a very thin, long box on it, and then another much thinner, much longer box. Enormously longer, but a great deal thinner, and so on and so forth, and another one over here, so that they very rapidly become extremely thin, the boxes, and you lay them out so that they get longer and longer, but thinner and thinner, in such a way that the total sum is very small. It's not difficult to show that instead of using boxes in the definition, we could have covered by small balls instead of by small boxes. The rough idea being that balls contain, every box lies in a ball and every ball lies in a box, and they aren't really all that different in volume. We've always used the definition in this class that a box should have its sides parallel to the axes in Rn, but you could also allow rotated boxes and it wouldn't really change the definition, which is again something you can prove without much difficulty. So it doesn't really affect whether the which measure sets are measure 0 if you allow measure 0 sets covered by these kind of boxes instead of those, or just allow these ones. The surprising aspect of the theory comes in when you notice that by rearranging sequences of sequences into a sequence, a standard trick, that that if you have a sequence of measure 0 sets, then their union has measure 0. Again, I won't do that in detail, but if you have a sequence of sequences, you have sequences, another sequence, and so on. What you do is something like this to go around all of the elements of the two sequences. You follow some sort of path like this, trace out into one sequence, so that makes a sequence of sequences into a sequence, and in that way you can easily see a sequence of measure 0 sets has measure 0 union. But that leads to the surprising fact then that as an example, the rational numbers sit inside the real numbers as a measure 0 set. So they're in some sense taking up no space at all, and yet they're all over the place. Every real number can be approximated as closely as we like by rationals, and yet they don't take up any space, so to speak. When I say space, of course, the word measure is used just to avoid the problem of that in the real number line, when we measure how big something is, how long something is, we use length. In the plane, we use area, and in three-dimensional space, we use volume. But there's no obvious name for n-dimensional analog of these things, n-dimensional volume, and so it became traditional to call it measure, to call all of these measure, one-dimensional measure, two-dimensional measure, three-dimensional measure. Hence the name measure 0 instead of volume 0 or length 0 or area 0. It's just a way to avoid having to pick one of these terminologies. I'll leave you to convince yourself that if we have a measure 0 set in, let's say, Rn, and then we have, well, let's suppose it lies in some open subset of Rn, and then we have a diffeomorphism p takes u to w, also containing Rn, then phi of a is also measure 0. Well, p of a is measure 0 if and only if a is measure 0. So it's invariant under let's say, well, this is under diffeomorphisms, right? So that's not completely obvious, but I'll leave you to consider why it's true. Partly because measure 0 sets aren't really what we want to talk about in this class. They really belong to more to functional analysis than they do to, or to classical analysis than they do to differential geometry. For the last basic result about measure 0 sets that we're going to need, we can consider there's a theorem that I won't prove because it's really a measures theory theorem. The idea being intuitively look in the plane at some set given by some measure 0 set given by a whole bunch of little things, and most of those things aren't vertical things. Then we could look at for each point on the real number line. So we have coordinates x and y, and we have some set. This is a contained in the plane. So a set of points in the plane, and then you could say that if a is, let's suppose a is measure 0 in the plane, then for each point on the real line, I want to picture what are all the points that live above it up here. If I take, say, this point here, I can look above it and look at the plane, and it'll hit various points of A. So I'll simply let AX be the set of points Y, so that the pair XY belongs to the set A. So that is the set of all y's that cross. So in this case, that's these 2 points here, these 2 y values. So what we want to say is that there exists a prime contained in the real axis, the x-axis. So there's a set a prime here, so that if x is not an a prime, then this ax is measure 0 in the real number line in the y variables. So so in our picture, what we're saying is that we have this some sort of set, and there may be some bits of it that are actually vertical, like here. It's a measure 0 set, say union of line segments, for example, measure 0. But when you look at this point here, your pre-image up there is not measure 0. So you failed to have measure 0 in this. So for this point x, this set ax here, it does not have measure 0. That's the ax here. It's these y values, and it doesn't have measure 0. So that could fail, and it could fail maybe somewhere else. Say over, for example, here, you might have a set which is not measure 0. But that only happens at these 2 points, and that's those 2 points constitute our set. Those 2 points constitute our set A prime of values at which something bad happens. This guy has vertical stuff of positive measure, but otherwise everywhere else it's just measure 0. And the same thing works, maybe I'll just say that the same thing works for, let's say, instead of 2, let's do P plus Q. X is now in RP, and Y is in RQ. Works for any number of variables. So this would be a measure 0 set in RQ. So we can do it in any number of variables. Okay, so that's an important observation. It's not saying that the image of A in the x variables is measure 0. Note that in this picture you can see lots of image. You've got this line segment here would have positive measure inside x. So when you project a measure 0 set, the projection can fail to have measure 0. This line segment here is measure 0 in the xy plane, but its projection down to the x line is not measure 0. But that's okay. We're not saying the projection is measure 0. We're really saying the pre-images of points are measure 0, typical points. So except for these 2 points, all the other points have, all the other points like this one have a measure 0 pre-images, vertical slices. So that's what we're talking about. Okay, so that's a theorem which, again, I won't prove. It's very different in character to the sort of things we want to deal with in this class, and of course it's a trivial consequence of much more general results proven in any course in measure theory. So if we want to think about manifolds, we have a funny problem that manifolds and measure zero sets. When we glue manifolds together, roughly speaking, we glue them out of our charts, which are somehow pictures of the local pictures of our manifolds, and then the charts are valued in the Euclidean space, and so they have some images and something like this. The problem is then there's now a transition map. The transition map might not preserve measure, in other words, volume or area or length or whatever the thing is we're measuring here. So that's bad. But the good thing is that it's a diffeomorphism. So it'll take measure 0 to measure 0, and vice versa. So it preserves measure 0. It doesn't preserve things of length 1 or area 2 or volume 3. It doesn't, volume 7, let's say, it doesn't preserve those, but it does preserve measure 0 sets. It takes measure 0 to measure 0. So therefore, we can simply define a subset of a manifold is said to be measure 0 if for all charts, say U phi of M, of the smooth structure of M, A, when we intersect it with U and plug it through phi, so we then would take the chart of the piece of A that lives inside the domain of the chart, and that should be measure 0 in Euclidean space. So that'll be a good enough definition. That'll cover the right results we need. It doesn't help us to measure length or area or volume. It doesn't help us to actually measure anything that's not measure 0. But anything that's measure 0 will be fine. It'll make sense, as it'll make a definition of such a thing. So next we want to think about a very elementary idea, which is just that we want to go back to calculus and draw very simple pictures. First of all, what does a function look like in calculus? And what does a critical point look like? If we take a function which has a critical point right here, and we think about what happens when we slightly perturb the x value, then the y value to sort of first order doesn't change. Because at a critical point, small changes in x that are some order h change y by h squared at the least. So when we make a tiny change in x, we vary x through some tiny little interval. We vary y through, as if the interval is very small and the x is the y interval should be even much smaller. And that's the fundamental idea here behind Sard's theorem. So here's the statement of the theorem of Sard. If we have a smooth map of manifolds, it just has to be smooth, not a diffeomorphism, with equal dimensional manifolds. Suppose that okay, so it just has to be equal dimensional manifolds. Then the set of critical values of phi, which is not contained in P, it's contained in Q, is of measure 0 in Q. Now let's get clear about why it is we're working in Q, not in P. So we have a map from P to Q, a map phi, and we're then saying that there's some measure 0 set of points in here where the thing is a critical value. In other words, where the pre-image is a critical point. Okay, so what was critical point? What was regular point? What was the definition again? Which I think we did cover. What's the critical point for a map of equal dimensional manifolds? Well, in general, we said that a regular point of a smooth map of manifolds of any dimensions, whether they're equal dimension or not, any dimensions, a regular point is a point P0 in P where phi prime of P0 is onto. That's the definition of regular point. And so a critical point is anything else, not regular. And so P prime is not onto. Okay, so that's the definition of a critical point. A critical value, well, let's say a regular value rather than a regular point, is a point Q0 in Q so that if some point P naught in P has value equal to Q naught, then P naught is regular. So what does that mean? A regular point is an input where the derivative is onto. A regular value is an output where any input reaching that output has to be regular. So all the inputs that go to P naught, that go to that output Q naught, have to be regular points. And then a critical value is any point value that's not regular. Okay, let's take simple pictures of these in one variable calculus to see what we're talking about. If we draw, well, let's draw another page of paper. So if we draw a simple one variable function, basically the same function we already drew, so it has some critical points. There's a critical point here, and I might want to put another one in. We could have local and global minimum or maximum. I don't really care about that. Minimum and maximum are not of interest to us at the moment. But what we're going to do is look at the critical points for the derivative 0 in one variable calculus. And that corresponds, of course, to our general definition. Those are the points that are not regular for this as a map thought of as this manifold, the real line, to this manifold, the real line. This is our P. This x-axis is the manifold P. The y-axis is the manifold Q. And all we're doing is looking at critical points in the usual sense of calculus, derivative equals 0. Because the linear map that gives us, that derivative gives us, is, of course, a 1-by-1 matrix. And a 1-by-1 matrix is not onto just when it's 0. So those are the critical points, right? So you have 3 critical points. And those are the critical points. And then what are the critical values? Well, this is a critical value. And then this is a critical value. And then this is also a critical value. So there are 3 critical values of this guy here. Okay, so now, and you can see that they're clearly measure 0 because there's only 3 points. So 3 points is certainly measure 0 in the real number line. We said that even a countable set of points was measure 0. So that's a measure 0 set. So it's correct. This is not very interesting. But let's take another look at almost the same example and see why it is that we're looking at critical values, these reds, not the greens. What's the difference between the values and the critical values and the critical points? We draw essentially the same picture, but I want to do it a little bit differently. I'm going to draw, let's say, the same function, except now I'm going to allow myself to go down here. Oops, it's not very well drawn. Let me do it again. So we'll take this guy and we'll draw, I want to do something like this maybe, and then like this, and then we'll go like this, and then it'll go flat for a while. That's okay, it can be that. Function can do that, it can be perfectly flat, and then maybe go up again. Okay, so now we have to look for critical points and critical values. Now critical points are where the derivative is 0. The derivative is certainly 0 here and here. But it's also 0 all the way all over this stuff where it's flat. And that whole region, you can see those are all critical points. So the critical points are this entire region here. It's all critical points. And then this guy's a critical point. So the critical points by definition are the inputs on the x-axis. Just inputs on the x-axis that have, where the function has derivative 0 in this case, or more generally for a manifold where the function's differential, or the differential of the map is not a linear submersion, not a linear surjection. So that's critical, and then this is critical. So this guy has 1, 2 critical points here, and then a whole range of critical points along here. And therefore the critical points are not measure 0 because they are the set is this 1 point here, this 1 point here, and then this interval here. So the critical points are not measure 0. Critical points, not measure 0. And that doesn't contradict Sard because Sard doesn't talk about critical points. He talks about critical values. If we look at the values, there's a value here, and a value here, the critical value here, and then there's all this, which is critical value here. There's only 3 critical values Because when you have this interval of critical points, the derivative is 0 all the way along the interval, so the value doesn't change. When the derivative is 0, the function's constant. So it doesn't have changing value. So there's only the one value, a whole range of critical points, but only one critical value, one critical value, one critical value. So we've got 3 critical values. And so it is correct. The Sard theorem is working perfectly well here. It's getting the right answer. There's critical values forming a measure zero set, but critical points not forming a measure zero set. So these are the critical values. Okay, so that's why we have to be careful about whether it's critical points or values we're looking at. And let's see if we can get into the proof of the Sard theorem. So the first observation we want to make about this problem is that since we said that if we had a union of measure zero sets as measure zero, that means that we can look at, if we have a map from some P to some Q, we only need really to cover it in countably many little charts, and we can then look at each chart independently and see what about the critical points and the critical values, and similarly cover Q in some countable collection of charts, and then just see what happens for each of the local little pictures of the map. Do we get measure zero critical values? And then we throw them together and get measure zero. So it's good enough to work locally. I only need to do this in local little pieces, but because locally the thing is identified with Euclidean space, the manifold, each manifold is identified with Euclidean space, we can just assume that loss of generator that P and Q are, let's say, bounded open sets in Euclidean space. We can assume our charts have bounded values inside some bounded open sets. So we could assume that P, for example, is something like a box, or we could even work with P actually being a box, although strictly speaking a box isn't actually an open set, but it's fine to allow us to work with a chunk of this open set P. Let's just say a box and just call it P just for simplicity of notation. Now I'm going to define a constant M, not meaning manifold, but just meaning maximum, which is the maximum for any point in that input point in the inputs in this P of the operator norm of the matrix phi prime. So remember that phi is our map. Phi takes P to Q. Now we'll make P be a box, and again it's not quite an open set anymore, it's not quite a manifold anymore, but it's a box inside some open set, also called P. Just to avoid notation, let's call it P. So we have this map, which is a smooth map, to an open set Q in Euclidean space, and we've declared M to be the maximum magnitude. What's the magnitude of a matrix? It just means the maximum stretch factor on a vector. Stretch factor when it linearly acts on a vector. So that's what I mean by this magnitude here, and I'm not going to prove it. That's bounded because we've made this thing be a box, so it's compact. They're a compact set of x's. There's one of these guys at each one, and they're varying continuously, which I won't prove. So I'll let you think about why that's continuous in the phi prime. In other words, why this norm of a matrix is a continuous quantity in the matrix. We can picture our P as being, I said, a box. So what we want to do is to think about what that box might look like. We'll cover that box in tiny little boxes by grid with a mesh size of delta. In other words, all the sides of all the little boxes are at most delta. And we make delta very, very small by making a very fine grid. If we make the grid really, really fine, then we can say that the nonlinear map phi is approximated by its linear approximation pretty well inside little tiny grid boxes. In other words, we can assume that in our grid boxes, phi of x minus, phi of, I've got a notation in my notes, phi of y minus phi of x for x and y in the same grid box, some little tiny box in the grid, that this guy is approximated pretty well by the linear approximation phi prime of x times y minus x. And we can assume that's very small. So we can assume, in other words, that this guy is very small. Let's see, less than or equal to some value epsilon times how far apart y and x are, and they're inside a grid box, which we can assume is so small that I said that sides should be less than delta. Let's make the mesh size so small that in fact this guy is less than epsilon times delta, just for notation purposes. And really the delta here should be the maximum length across the grid box, which is from one corner to the other. But let's just make the mesh size so much smaller, let's say much smaller than delta, so that this becomes less than epsilon delta, because that's what I've got in my notes, so I don't want to mess it up. So we've made sure that points that are very, very close together in tiny little boxes, approximately the map is approximately its linear, given equal to its linearization, and the error is little o of this quantity, so we can write it as some epsilon times this times the difference, or the epsilon times the distance across the little tiny grid box. Now suppose we start with a grid box with a critical point inside some, let's say x, inside some grid box. One of these little tiny grid boxes has a critical point in it. What we want to calculate is the volume of the image of, let's say, so inside some grid box capital X. And capital X will be one of the many grid boxes inside P. It'll be a tiny little grid box that happens to contain a critical point. So we want to calculate out this volume, or estimate it. That's the problem. So we want, in other words, we're calculating the volume of the image, and we're going to try and show that we can cover the image in little tiny boxes, the image of the critical points. So the image of the critical points is the critical values. We want to show we can cover them in little tiny boxes. So in order to do that, we need to just make sure this thing is very small, that it's being covered in a little tiny box. Just for the sake of notation, we can just make the critical point we're interested in, be 0 by translating whatever point it is to 0. It doesn't change volumes of anything. And we can also assume that phi of 0 is 0, because we can translate the output of that point to wherever we want without changing the volume of this quantity here by just translating it all around. It doesn't change volumes. So then what we want to think about is the fact it's a critical point. So now we've said, well, 0 is critical, x equals 0 is critical. So that means that this phi prime of 0 is not an invertible matrix. It has determinant 0. Okay, so what happens when you have a determinant 0 matrix? What do we know about determinant? It's the size of volumes of boxes. If we take a little box, our little grid box, this is x, our tiny little grid box, this is the origin, and what we're doing is we're going to throw this map through phi prime, and we get some phi prime of x, which is no longer, so this is a nice three-dimensional picture. This guy, because phi prime is determinant equal to 0, phi prime is at 0 is 0, so this is phi prime 0. It's a linear map with determinant 0 because it's a critical point, and it's a square matrix, so to be critical means that it's not onto, not as a linear map. Square matrix is not onto. That means it has determinant 0. That means it takes this box and squishes it flat into something that, if you think about it, has 6 sides. The image of a box, of a three-dimensional box under a linear map, will be some 6-sided figure, but it doesn't really matter. What matters is just that it sits inside some kind of flat thing. So it squishes the box flat. Phi prime of 0 squishes the box x flat to lie in some plane. So phi prime of 0 applied to the box x lies in some w, some linear subspace contained in Rn. Linear subspace. Okay, so we've squished the box flat, so dimension w is less than or equal to n minus 1. It's a smaller dimensional subspace. Okay, so now what I can say here is that I had this equation, phi of y minus phi of x. It's approximately the linear guy. So I know what the linear guy does. It squishes the box flat. What does the nonlinear guy do? Well, it approximately does the same thing. It nearly does the same thing. That's the box being squished flat, and this is what the actual map phi is doing. It's almost the same thing. I could probably put a 0 in here. That might make it a little easier. if I get rid of 0, that's this guy. So this is what's happening to our box. This is y in our box. And then this is what's happening to the actual thing, and phi of 0 is 0, so that's also 0. So it simplifies a lot. We find this guy, phi of y minus phi prime of 0y, is very, very small. Okay, so they're nearly the same thing. And so we can say that that phi of x therefore lies inside a a set of distance at most epsilon delta from set of most epsilon delta from phi prime of 0x. They're almost the same thing. So we have this very simple picture that we're changing the nonlinear map and the linear map are almost exactly the same thing. They're very, very close to each other all the time. And so this guy isn't very thick. The linear map flattens us out into a flat subspace W. The nonlinear map must stay close to that subspace. So I want to imagine in a picture that the linear map is taking this box X and flattening it out into some linear subspace. Perfectly flattening it out linearly. Then that's the phi prime of 0 map to the box X. The phi of 0 map does almost the same thing, so just phi of x, and it should be almost the same guy, so we could draw the same picture exactly and then say, well, it's not far away. So so it's a little bit thickening of that, maybe a little bit thicker. So it's not much different. Now we can rotate without affecting any volumes, so we might as well, without loss of generality, we can assume that our subspace W, that this thing lives inside, this is inside some linear subspace W, we can assume that this guy is just 0 cross r n minus 1. So the first coordinate gets squished completely. Now it's convenient to then take a notation up where it's convenient to say that XR means a box, any box. I won't specify which box. What are we doing? XR is any box whose sides are at most length R. Okay, so well, let's say all of whose sides are length R, just for simplicity. Okay, and then similarly, we'll write something like BR is a ball of radius R. I won't specify where the center of the ball is or which box this is, just to make it not too confusing, because there are just too many center points to worry about. So if I write something like B of R is contained in X of 2R, I mean by that statement I could mean every ball of radius R lies inside some box of side lengths 2R, for example. We've started out with our little box, which was our box X, and we said but we wanted all of its sides to have length delta. But that puts it inside a ball of slightly larger radius, which you can check to be radius square root n over 2 times delta. And therefore phi prime at 0 times the box of radius, this guy, is contained in, well, it's contained in this linear subspace W, which means the first coordinate is just 0. We've arranged by rotation. Crossed with a ball. Well, the balls stretch only by a factor of m. We said m was the stretch factor. So if that's our radius ball input, our radius output could only stretch by at most this guy. Delta was root n over 2. And that's contained inside some box of size of the, let's see, what size do I need to do? Okay, yeah, twice that. So m delta root n plus we had a little bit more because of the problem that we have to worry about the thickness. Sorry, no, we don't need that. No, sorry, the ball is insane in the box of this size. Okay, so so now what we need to do is figure out what happens with our nonlinear map. We have phi of our box of size delta is contained in, well, an interval minus epsilon delta to epsilon delta because it got a little bit further away from the linear map by only this factor, crossed with the the same box we had for the linear factor, but we have to put a 2 epsilon delta because it might stretch out a little bit off the, up and down, and this is off to the side. So it's going to go a little bit away from there. Okay, and therefore this guy lies in a box of volume, of volume at most, and we just have to calculate the volume of this box, which turns out to be 2 epsilon delta to the n, and just multiply this many times, however many times you need this thing times the length of that thing, and so volume of a box is not hard, right? Product of the side lengths, and then it'll turn out to give you this guy to the n minus 1. Okay, so that tells us that when you have a critical point, the center of this box x delta, somewhere in this box at x delta, doesn't really matter whether it's in the center or on one of the vertices. You have this critical point of this guy somewhere inside this box. Then it lies inside its image under phi, lies inside a very small box of this size. The crucial point here is this epsilon. The rest of it is really irrelevant because if you didn't have a critical point, you wouldn't get the flatness in these directions, and so you wouldn't get the epsilon factor here. We now just have to add up over all the little tiny grid boxes. We said that we assumed more or less that P itself, our input manifold, was a box, and we had lots and lots and lots of tiny grids. We only worked out what happened in one of them, and now we have to add up. We only have to add up over the ones that contain critical points, though, but we add up over all of them, and then we can get an estimate on how bad this gets. The total volume, when you add up all such boxes, assuming that they all have critical points in them, which is the worst you could have, then the total volume covering of these boxes, that covering all the critical values, they're not covering inputs, they're covering outputs, right? The phi of this guy. Output is covered by something of this size. Total volume that you need to cover it all up, I'll just add them all up, 2 epsilon times the volume of, this is the volume of the box P, times m root n plus 2 epsilon to the n minus 1. And we can make this thing be as small as we like by choosing delta small enough and to make epsilon very small. So we choose our delta very, very small, and that'll make epsilon very, very small, and we can make this go to 0. Okay, so that's the proof. It's very, very clever, but the fundamental idea is simply that when you have a linear map that squishes something flat, then a nonlinear map not far away nearly squishes it flat. And so that's what happens near the critical points, and that's why Sard's theorem works. There's a serious application of this, which I won't go into detail. The lecture notes give the detailed version of this. It gives us a problem with some solution in it. You can consider M as a contained, let's suppose, as a surface contained in R 100-dimensional space. Then, so you have a surface M contained in a 100-dimensional space. Then it's not hard to show. Again, it's a nice series of problems for you to try, and which I think have solutions in the back. Then you can show that in fact you can take it in its 100-dimensional space and project it onto some linear subspace by some orthogonal projection, orthogonal to some vector, into a 99-dimensional space, and so on and so forth. And if you're careful about how you do it, you can use that Sard theorem to show that it actually embeds into the lower dimensional space, and keep going and going and going and going until it turns out you can't keep going until you get past down to R5. So if we have a surface in a 100-dimensional space, you can always project linearly until eventually it becomes a surface sitting inside 5-dimensional space. So if there is some embedding of this thing into, well, not necessarily 100, but let's say 1 billion or 1 trillion dimensions, then there is some embedding of the surface into 5 dimensions. And that's a nice example of applying this technique. But again, I haven't explained how it works, but it's explained in more detail in the lecture notes. We want to use Sard for various reasons. Basically, we want to try and perturb things into some sort of general position, and so the fundamental fact here is that if phi takes P to Q is a smooth map of manifolds that don't have to have the same dimension anymore, then so they could be any dimensions, then there exists a measure 0 set, a prime containing Q. This is almost exactly the same thing I said about Euclidean space previously, so that so this is an exercise for you to try, so that for all Q in Q minus A prime, away from that nasty set, the fiber, which we'll call PQ, which is phi inverse of the set of Q, that's just like my notation before. So we have this somehow this Q, and we have this some P, and we take a point here. We look at all the points that map to it. That's called PQ. This is Q. This guy has intersection A intersect PQ contained in PQ of measure 0. It's measure 0 in PQ. So that's a nice fact, which I'll leave you to check why it's true. It's essentially the same thing I already said about Euclidean space, so it's not hard. So let's see if we can use this to do something not completely obvious. So as an example, how can we avoid things? We want to avoid things. Let's see. So some example of avoiding things. Let's take, let's say, the plane, and let's let P, let's let P be the plane minus the origin, and let's let Q be the real projective line, which remember is the set of lines through 0 in the plane. So the picture, that's all of the lines that go through 0, all of them, right? And Q is the set of such lines. So each point in Q is as a line, is a line through the origin in the plane. So that's one of these L's. So Q is some abstract manifold. We showed that it's a manifold. Now what we can do is simply to map phi takes P to Q by the obvious map phi of a vector V, which is non-zero, because P consists of non-zero vectors, is the line through 0 and that vector. So the line through 0 and that vector. So we're saying that if you take a vector V, you can find the line through the origin that contains it. That's L. So you take the vector V and you substitute L. Phi of V is L. So that's the map, and we know that's actually a smooth map. And what we can then say is that by this previous result, if we take A inside R2, any measure 0 set, then by the previous result applied to this phi map, you can say there exists some A prime subset of Q, measure 0. So a measure 0 set of lines, so that if some line is not in that measure 0 set, then the line intersects the set A in a measure 0 subset of the line. So that in the picture says that if we have very few points in our measure 0 set, then we can typically most lines, some lines may, like this line, this horrible line here, happens to choose to intersect that set in a very large set. That's bad. but the other lines don't. Typically, most lines don't. So if you have a set that typically most points aren't going to touch, then typically most lines don't touch it except for a set of measure zero points on those lines. So most points of most lines don't touch the set of measure zero. So if you have a set that most points don't touch, then most points of most lines don't touch that set. It's intuitively clear, but it's something we can see comes out naturally from this kind of description of thinking about measure zero sets and their projections. So our aim is to try and avoid sets. Let's say that we want to talk about sets being large or small. A subset A contained in a manifold M has dimension at most k if there exists a sequence S1 to S2 of let's say embedded, just to be careful, embedded submanifolds of M with all of them having dimension, all of them less than or equal to k, and with A contained in the union of them. So you can cover it in sets, in a sequence of sets of most that size. So this is very close to our notion of measure zero. It's very natural to think about covering not with little boxes, but in this case covering with little skinny things of a certain dimension, holding down the dimension. So as an example, the rational numbers are countable, and so they have dimension 0 because, according to this definition of dimension, because you can put them in a sequence, and so a sequence of zero-dimensional submanifolds, a sequence of points. For those familiar with the Cantor set containing the real numbers has dimension 1, and according to this definition, you can cover it with one-dimensional intervals, but you can't cover it with just a sequence of points. It's not countable. The more interesting examples of these kinds of sets are the solutions of equations. Let's look at a simple equation, the Whitney umbrella. I won't go into a lot of detail, but it's the set of points in three-dimensional Euclidean space satisfying the algebraic equation x squared equals y squared z. And it's a strange object to look at. It looks something sort of like this. Not a very good picture, but it looks something like this with a sort of a vertical strip along there, and is that good? And then it has a line through it as well. It has this line going through it. Now this guy is covered in. It has a smooth surface, which consists of the points z equals x squared over y squared. You can see the equation by dividing by y, with y not 0, and that's this nice smooth surface. And then it has a line where you're not on the surface. You have to have y equals 0. You plug y equals 0, you get x is also 0. And so this is the line whose equation is x equals y equals 0. So you have two pieces of straight line and a surface. So this is an example of something that's not a manifold. It's worse than a manifold, but it is a union of an embedded submanifold here and a line here. The embedded submanifold is not closed, though. The closure, this embedded surface, this nice smooth surface, the closure contains some of these points here along this line, so it's actually a bit nasty. So that's an example of something that's a bit worse than a manifold, but that is covered by a sequence of submanifolds. And so this guy has a dimension. Dimension of the Whitney guy is 2 according to this definition. It's maybe not the most general or most useful definition of dimension, but it'll do for us for what we want to do in these lectures. There's a generalization of this which I don't want to write about or talk about in much generality. But you could take, instead of these algebraic equations, you could take any collection of analytic equations, that is to say equations in real or analytic functions, so given by convergent Taylor series, and you can say that the same sort of thing works, that these objects are somehow unions of manifolds of various dimensions, but we don't want to really do that in our situation. So you could do much more general things and get some kind of notion of dimension out of it. So Whitney is a good enough example for us to get a sense that there are objects out there that have a dimension in this sense that are not manifolds. So here's the main trick that enables us to get some kind of transversality results. We'll say that a map phi takes P to Q is transverse. So we had already transversality of manifolds out of maps. What if we have just a map, but we have a set? It's transverse to a set S contained in Q if S is it can be written as a union of a sequence of submanifolds. So that it's a union of a sequence of embedded submanifolds, and phi is transverse to all of the SIs. Okay, so that'll be our definition of transversality for more general sets, somewhat nastier than submanifolds, and it'll allow with things like the Whitney umbrella. Now here's an easy result using this notion of transversality so it's a simple lemma S contained in P, subset, can be any subset, and then phi phi takes P to Q is a smooth map. Then for all Q and Q outside some measure zero set, except on a measure zero set, the fiber, again, fiber PQ is defined to be phi inverse of the set of Q, all the things in P that map to Q, so it's written P sub Q, so that I remember that it's all the things in P that map to this point Q, is transverse. Transverse to that's the whole set S. Okay, so that's a useful result. It's not a very hard result to get. So the proof is, well, we write S as a union of these SIs, and we only have to check for each SI. By definition of transversality, it has to be transverse to each of the SIs. But checking each one it just means that we might as well, without loss of generality, can assume that S is one of the SIs. Is an embedded submanifold. So that's nice because we now get rid of arbitrary sets and work with embedded submanifolds. So now what we do is we just take out, cut out from Q a measure zero set of points where phi is not where phi is critical, let's say. So we can assume we're working at regular points, and then also where phi restricted to S, which takes S to Q, is critical. That also is a measure zero set. So we've cut out the critical points of the map of phi mapping from P to Q, and also the critical points of phi as a map from S to Q, restricted to S. So we can assume we're dealing with points at which phi restricted to S has full rank differential, and phi has full rank differential as well. And then you can just check in coordinates. It's rather easy to do. I won't do the rest of it. You just compute out what does it have to look like, because it's now a regular map at those points. We're now dealing only with regular points. And so we're dealing with regular points of both the map phi and the map phi restricted to S. And so you can check that regular points for both maps, you ought to always get transversality. So we've now got a way to produce transversality to ensure we can construct transversal objects. We want to use this way next time to try to see if we can wiggle objects which aren't transversal into objects which are transversal.